We're going to determine if the series summation n equals 5 to infinity of natural log of n divided by n squared plus n plus 1 converges or diverges. First, we'll try using comparison test, which I'll abbreviate by CT. We'll need the following result. Recall that natural log of n is less than n and greater than 1. Since our series starts at 5, all we care about if this is true for n greater or equal to 5, and this certainly is true. So natural log of n divided by n squared plus n plus 1 is less than n divided by n squared plus n plus 1 and is greater than 1 divided by n squared plus n plus 1 for any n greater than or equal to 5. And if we sum these up, summation n equals 5 to infinity natural log of n divided by n squared plus n plus 1, that's less than the summation n equals 5 to infinity of n divided by n squared plus n plus 1, and this is greater than the summation n equals 5 to infinity of 1 divided by n squared plus n plus 1. So is this inequality helpful to determine if our series converges or diverges? Let's start with the series on the right. The series on the right, the highest power of n in the denominator is 2 and the numerator is 1. We'll use limit comparison test to compare the series with the kind of modified harmonic series, summation from 5 to infinity of 1 over n. Since this series diverges, so is the series on the right. So our series here is less than the series that diverges. That doesn't help because our series could certainly converge because a finite number is, any finite number is less than infinity, or it could also diverge. That would mean that it grows slower to infinity than the series on the right. So no information we can extract from the fact that our series is less than a diverging series. Now let's look at the series on the left. The difference in the highest powers is 2. We use limit comparison test to compare it with this modified p series, summation from 5 to infinity 1 over n squared. Because the series converges, we can conclude that our series, or the series on the left, also converges. Again, this series in the middle is bigger than the series that converges. It could be a converging series, just the sum is higher than that of a series on the left, or it could be infinity. It could also diverge. So comparison test, the way we looked at it here, is of no help. It doesn't help us to determine if the series converges or diverges. So now let's move on to the limit comparison test. We're going to call our series summation from 5 to infinity natural log of n divided by n squared plus n plus 1. We're going to call this series the a sub n series, the summation from n equals 5 to infinity a sub n. Now recall limit comparison test. It works like this. We're going to have a b sub n series. So in this case, it'll be summation from 5 to infinity b sub n. And of course, a sub n and b sub n must be positive. If the limit as n approaches infinity, a sub n over b sub n is equal to L, then there are 3 possible cases of limit comparison test. Let's call this case A, L being positive and finite. It means then that the a sub n series and the b sub n series both converge, or the a sub n series and the b sub n series both diverge. Case B, the second possibility, is if L equals 0 and b sub n series converges, so does the a sub n series. And case C, if L is, the limit is infinite and b sub n series diverges, so does the a sub n series. So now let's try various series for the choice of b sub n. Let's try b sub n series n equals 5 to infinity, b summation from 5 to infinity of 1 over n, a modified harmonic series. And that's because natural log of n is less than n and greater than 1. So if it's closer to n, the difference in the highest powers will be closer to 1, so we can compare it to this 1 over n series. Let's look at the limit as n goes to infinity of an over bn, so it's natural log of n divided by n squared plus n plus 1 divided by 1 over n, and this is equal to the limit n approaches infinity of n times natural log of n divided by n squared plus n plus 1. Let's first divide everything by the highest power of n that we see, which is n squared. This is the limit n goes to infinity. Natural log of n over n in the numerator, and the denominator we have 1 plus 1 over n plus 1 over n squared. Notice that the denominator as n goes to infinity goes to 1, so this limit is the same as the limit as n approaches infinity of ln of n over n, and that's the same as limit as x approaches infinity of ln of x over x, where these are continuous functions. We see that we have infinity over infinity as an indeterminate form. We can apply the L'Hopital's rule, and this gives us the limit x goes to infinity. The derivative of the numerator is 1 over x, and the derivative of the denominator is 1, so this limit is 0. So we are under case B if our L is 0, but in order for case B to work, the Bn series must converge. But in our case, our Bn series is the summation 5 to infinity of 1 over n. This series diverges, so limit comparison test does not apply. We cannot draw any conclusions. So this didn't work. Now let's try another choice for summation from 5 to infinity of b sub n, and this time we'll try that to be the summation from 5 to infinity of 1 over n squared. So now the limit as n goes to infinity of a sub n over b sub n is limit n goes to infinity natural log of n divided by n squared plus n plus 1 divided by 1 over n squared, which is equal to the limit as n approaches infinity n squared natural log of n divided by n squared plus n plus 1. Once again, let's divide everything by highest power of n. This is limit n goes to infinity. We have ln of n in the numerator, and the denominator we have 1 plus 1 over n plus 1 over n squared. Once again, the denominator goes to 1. The numerator ln of n goes to infinity, so this limit approaches infinity, and we're under case C because our L is equal to infinity. For case C to work, the series, the b sub n series, must diverge, but our b sub n series is the summation from 5 to infinity of 1 divided by n squared. It converges, so again case C does not apply, and we have to try something else. So the thing we're going to try now, everything so far has failed to help us find if the series converges or diverges. Let's try a power of n that's between 1 and 2. So we'll try the summation from 5 to infinity of b sub n to be the series, the summation n equals 5 to infinity. Let's try 1 divided by n to the 3/2 power. And so now the limit n goes to infinity, a sub n over b sub n is equal to the limit as n goes to infinity, natural log of n divided by n squared plus n plus 1 divided by 1 over n to the 3/2 power. And this is equal to the limit n goes to infinity, n to the 3/2 times ln of n divided by n squared plus n plus 1. Once again, the highest power of n that we see is n squared. Let's divide everything by n squared, and this gives us the limit as n goes to infinity, ln of n over square root of n to the 1/2, and in the denominator we have 1 plus 1 over n plus 1 over n squared. Once again, the denominator goes to 1. We're left with the limit as x goes to infinity, ln of x divided by square root of x. This is infinity over infinity. We apply L'Hopital's rule, and this gives us now the limit x goes to infinity, 1 over x divided by 1 over 2 square root of x, which is limit x goes to infinity, and this is 2 over square root of x. This limit goes to 0. This is our L. We're now back in case B, but this time our Bn series is the summation n equals 5 to infinity of 1 divided by n to the 3/2 power. This is modified P series, that is P series with a few missing terms, with P equals to 3/2. This series converges, and we'll be able to conclude that the series we were examining, that is the summation n equals 5 to infinity of natural log of n divided by n squared plus n plus 1, converges, and this is by the limit comparison test. For more videos, visit www.mathprepvideos.com.